The cabin looked like it was wearing a coat. That's what people said when they saw what Anders Lindgren was building in the forests of northern Minnesota in the autumn of 1879. While every other settler was finishing their single-wall log cabins for winter, Anders was building a second wall around his entire cabin, an outer shell of boards, standing 6 inches away from his log walls, creating a gap that would be filled with something his neighbors considered worthless. Sawdust? They called it Lindgren's double cabin. They said the Finn was building 2 houses when one would do. Some suggested he didn't understand that wood was meant to keep cold out, not trap it between walls. Others shook their heads and predicted the whole contraption would rot from moisture trapped in the sawdust or become a fire hazard when the dry wood chips ignited from a single spark. The consensus was harsh and universal. Anders Lindgren was wasting lumber, wasting sawdust, and wasting time on a construction method that made no sense. Anders just kept working, board after board, nailing vertical planks to a frame that stood 6 inches outside his log cabin walls, creating a shell that would encase his home completely. And between the inner log walls and the outer board shell, he was pouring sawdust, wheelbarrow after wheelbarrow of fine wood chips and sawdust from the local sawmill, material the mill gave away for free because they considered it waste. Material Anders knew was one of nature's finest insulators. His neighbors were certain he'd created multiple disasters. Sawdust is flammable. One spark and the whole wall cavity will smolder for days, then burst into flame, and it will compact and settle, leaving gaps at the top, and moisture will rot it, and mice will nest in it. Anders Lindgren had built a fire trap, a rodent hotel, and a rotting failure all in one ridiculous wooden shell. Then January of 1880 arrived with cold that redefined what Minnesota winter meant. 40 below zero became commonplace, 50 below wasn't unusual. And on January 12th, the thermometer showed 54 degrees below zero, 54 below. The coldest temperature the region had ever recorded. Cold that killed livestock instantly, cold that froze wells solid, cold that made human survival seem impossible. In log cabins throughout northern Minnesota, families fought desperately for survival. Fires burned constantly, consuming cords of wood each week. Interior temperatures struggled to reach 30 degrees despite flames so hot they warped stovepipes. People slept in their coats under piles of blankets. Children cried from the relentless, penetrating cold. The battle was being lost. In Anders Lindgren's cabin, wrapped in its wooden shell, with 6 inches of sawdust insulation filling the gap, the temperature held at 64 degrees. 64 degrees with a fire so modest it burned for just 3 hours each evening. The sawdust, packed between the walls and dismissed as worthless waste, was trapping heat like nothing else available. The cabin stayed 30 degrees warmer than the log cabins around it. 30 degrees that meant the difference between desperate survival and actual comfort. This is the story of how Finnish forestry knowledge transformed frontier building, how sawmill waste became the most valuable insulation material on the frontier, and how the man they called crazy for building a wooden shell around his cabin was actually the only builder who understood what true insulation required. Anders Lindgren was born in 1844 in the forests of central Finland near the town of Jyväskylä. He grew up in a world where winter lasted 7 months and temperatures of 30 or 40 below zero were routine survival challenges. His family had been foresters and sawmill workers for generations. They didn't just cut timber. They understood wood in all its forms. In Finland, sawmills produced enormous quantities of sawdust and wood chips as byproducts of lumber production. Early sawmill operators viewed this material as waste, something to be burned or dumped. But Finnish builders had discovered that this waste had remarkable properties. Sawdust, when dry and packed properly, was an excellent insulator. Anders' father had worked at a sawmill that supplied lumber for building throughout the region. He'd taught Anders about the insulating properties of different materials. Wood itself has some insulation value, but solid wood conducts heat much faster than people realize. Sawdust, however, is different. Each particle of sawdust is separated from the others by tiny air spaces. Those air spaces, millions of them, prevent heat from conducting through the material. The result is insulation far superior to solid wood. Anders had helped build storage buildings at the sawmill where root vegetables were kept through the winter. These buildings used double wall construction with sawdust packed in the cavity between walls. The sawdust insulation kept the interior temperature stable. Vegetables didn't freeze in winter and didn't overheat in summer. The buildings required no heating, just the insulation provided by 6 or 8 inches of packed sawdust. He'd also seen residential applications. Some Finnish homes in the coldest regions used sawdust insulation in their walls and attics. These homes stayed remarkably warm with minimal fuel consumption. The sawdust, properly installed and protected from moisture, lasted decades without degradation. It didn't settle as much as people feared if packed correctly. It didn't attract rodents if the wall cavities were properly sealed. And while flammable if exposed to open flame, it didn't pose fire risk when enclosed between walls. When Anders emigrated to America in 1874, he worked in logging camps in Michigan and Wisconsin. He saw American building methods and was surprised by their inefficiency. Single-wall log cabins might look solid, but they provided minimal insulation. Heat poured through log walls almost as readily as it moved through the air. In Finland's coldest regions, such cabins would be considered death traps. By 1878, Anders had saved enough to file a homestead claim. He chose northern Minnesota, attracted by the timber and reminded of his Finnish homeland. But he immediately noticed the same pattern he'd seen elsewhere. American settlers built single-wall cabins and then struggled to heat them. They burned enormous amounts of firewood and still barely stayed warm. The waste of fuel and human effort was staggering. His claim was in a heavily forested area near a small sawmill. Perfect, Anders thought. Timber for construction and free sawdust for insulation. He would build the way Finnish foresters built in the coldest regions. Double walls with sawdust insulation, a cabin that would stay warm with minimal fuel. He filed his claim in the spring of 1879 and began construction immediately. First, he built a conventional log cabin, good timber, tight construction, 14 feet by 18 feet, solid and well built by any standard. But Anders wasn't finished. This log cabin was just the inner structure. The real work was yet to come. His nearest neighbor, a logger named James McKinley, whose claim adjoined Anders's to the south, watched the log cabin construction with approval. "Lindgren, that's a fine cabin you're building. Good, tight logs. Should keep you warm this winter." Anders smiled. "This is just the beginning. I build outer shell next." McKinley frowned. "Outer shell? What do you mean?" Anders explained. "I build second wall outside this cabin, 6 inches away, then fill gap with sawdust. Makes very good insulation." McKinley's expression shifted from confusion to disbelief. "You're going to build another wall around your cabin and fill the gap with sawdust? That's the craziest thing I've heard. Why would you waste lumber on a second wall?" Anders tried to explain the principle. One wall of logs provides some insulation, but not much. Heat moves through solid wood quite easily. But if you have airspace with sawdust, heat cannot move through so easily. Sawdust has millions of tiny air pockets. Air is very poor conductor of heat. 6 inches of sawdust insulates much better than 12 inches of solid wood. McKinley shook his head. "Sawdust is mill waste. It's got no value. And it'll cause problems. It'll rot with moisture. Mice will nest in it. And it's flammable. You'll create a fire hazard." Anders was patient. If sawdust stays dry, it does not rot. If wall is sealed properly, mice cannot enter. And when sawdust is packed between walls, there is no air, for fire is safe. McKinley left unconvinced, certain Anders was making a serious mistake. He told others about Lindgren's plan. The consensus formed quickly. The Finn is going to build a second wall around his cabin and fill it with sawdust. Doesn't understand that sawdust is waste material. Going to create a rotting, mouse-infested, fire-hazard cabin. The mockery was constant. Anders continued working, undisturbed by the criticism. By late August, he'd completed his log cabin. Now he began the outer shell. He built a wooden frame 6 inches outside the log walls, vertical posts at regular intervals connected by horizontal bracing. This frame would support the outer wall boards. Then he began nailing boards vertically to the frame. These were rough-cut boards from the local sawmill, about 8 inches wide and 1 inch thick. He fitted them tightly together, creating a continuous outer shell. The boards ran from just below ground level to just above the log cabin's roof line. When complete, the outer shell completely enclosed the log cabin, leaving a 6-inch gap between the two walls. At the base, Anders installed small drainage holes to allow any moisture that might accumulate to escape. At the top, he left small ventilation gaps to allow air circulation. This would prevent moisture buildup in the sawdust. The system was designed to keep the sawdust dry indefinitely. Then came the sawdust. Anders had arranged with the local sawmill to take all their sawdust for free. The mill was happy to give it away. They usually just piled it up and eventually burned it. Anders arrived with a wagon and loaded it with sawdust. Trip after trip. Hundreds of pounds of fine wood particles. He'd left gaps in the outer wall at regular intervals. Through these openings, he poured sawdust into the cavity between the inner log wall and the outer board shell. He poured carefully, tamping it down occasionally to ensure good packing, but not compressing it too much. Compressed sawdust was denser and therefore had fewer air pockets and less insulation value. He wanted it packed firmly, but still maintaining its fluffy texture. James McKinley visited during this process. He stood watching Anders pour wheelbarrow after wheelbarrow of sawdust into the wall cavity. "This is insane, Lindgren. You're filling your walls with garbage, with waste from the mill. How is this supposed to help anything?" Anders paused in his work. "This sawdust will keep my cabin warm, better than anything else available. You will see when winter comes." McKinley pointed to the sawdust. "That stuff will settle and compact. You'll have gaps at the top of your walls within a year, and moisture will get in there and it'll rot, and mice will burrow through it like it's not even there." Anders shook his head. "I pack it correctly so it does not settle much. Walls are sealed so moisture cannot enter, and mice cannot get through sealed walls." McKinley left, shaking his head. He told others, "Lindgren's filling his walls with sawdust. Actual sawdust from the mill. Says it's for insulation. Must not understand building." The story spread. Within a week, Anders's sawdust-insulated cabin had become the subject of amused conversation throughout the settlement. By mid-September, the sawdust filling was complete. Anders sealed the remaining gaps in the outer wall. The cabin now had an inner wall of logs, 6 inches of packed sawdust, and an outer wall of boards. The total wall thickness was about 18 inches, combining the log wall, the sawdust gap, and the board shell. He'd also extended this insulation to the roof. Over his log cabin's ceiling, he'd created an attic space and filled it with 10 inches of sawdust. The roof insulation worked on the same principle. Sawdust trapped heat rising from the living space below. The finished cabin looked unusual. The outer board shell gave it a different appearance from conventional log cabins. It looked smoother, more finished, but neighbors who knew about the sawdust inside viewed it with skepticism. That's Lindgren's sawdust cabin, double walls filled with mill waste. Going to be a disaster. What the settlers didn't understand was the science Anders had applied. Heat moves through materials through conduction. The rate of conduction depends on the material's thermal conductivity. Solid wood has moderate thermal conductivity. It conducts heat faster than many people realize. A 12-inch log wall provides an R value, a measure of thermal resistance, of perhaps R12 to R15. Sawdust, by contrast, has very low thermal conductivity due to all the air spaces between particles. Properly installed sawdust provides an R value of approximately R3 to R4 per inch. Anders's 6 inches of sawdust provided an R value of roughly R18 to R24. Combined with the log wall's R12 and the outer board shell's R1, his total wall R value was approximately R31 to R37. This meant his walls were 2 to 3 times more thermally resistant than a conventional log cabin wall. Heat loss through his walls was 1/3 to 1/2 the rate of standard construction. The fuel savings would be proportional. The first test came in November. Temperatures dropped to 15 degrees at night. Anders lit his first fires in his small cast iron stove. The cabin warmed quickly, very quickly. The thick insulation trapped heat so effectively that a modest fire raised the interior temperature to 65 degrees within an hour. At night, he let the fire die. In a conventional log cabin, the temperature would drop rapidly. In Anders's insulated cabin, it dropped slowly, very slowly. By morning, it was still 58 degrees, 7-degree drop overnight, with no fire. He mentioned this to James McKinley during a chance meeting. McKinley was skeptical, but curious. "Your cabin stays warm overnight with no fire?" Anders nodded. "The sawdust insulation prevents heat from escaping. Cabin cools very slowly." McKinley frowned. "It's early November. Wait till real winter. Then we'll see how well your sawdust works." December brought serious cold. Temperatures dropped below zero and stayed there. Anders maintained his routine, a fire each evening for about 3 hours. The cabin warmed to 65 or 70 degrees. He let the fire die overnight. The temperature dropped to perhaps 55 by morning, comfortable enough with blankets. Another fire in the morning brought it back to 65 quickly. His firewood consumption was remarkably low, perhaps 1/4 of what his neighbors were burning. They had fires going day and night, constantly feeding wood to maintain minimal warmth. Anders burned 3 hours in the evening, maybe 2 hours in the morning, and that was sufficient. James McKinley noticed the smoke pattern. Lindgren's chimney barely smokes. Can't be staying warm with so little fire. But travelers who stopped at Anders's cabin reported something different. The Finn's place is warm, really warm. That sawdust insulation must be working. Then came early January 1880. The cold that descended on northern Minnesota that month was historic. A massive Arctic air mass settled over the region and intensified. On January 8th, the temperature hit 35 below zero. On January 10th, it reached 45 below. And on January 12th, 1880, the thermometer showed 54 degrees below zero, the coldest temperature ever recorded in the region. In conventional log cabins throughout the territory, conditions became catastrophic. Stoves burned red hot, consuming wood at unsustainable rates. Interior temperatures struggled to reach 28 to 30 degrees. Families wore every piece of clothing they owned indoors. Water froze in buckets next to stoves. Frost formed on interior walls despite constant fires. People were surviving, but barely. The cold was so extreme it seemed to penetrate everything. James McKinley's cabin reached a maximum of 29 degrees with his stove burning constantly. His family huddled near the stove, the only source of heat. The far corners of the cabin were below zero. Ice formed on the walls. They were burning 4 cords of wood per week, an impossible rate to sustain. The firewood supply was disappearing. Fear was constant. In Anders Lindgren's cabin, wrapped in its wooden shell with 6 inches of sawdust between the walls, life was dramatically different. Anders maintained his normal routine. Evening fire for 3 hours. Morning fire for 2 hours. The cabin temperature ranged from 64 degrees after the evening fire to 56 degrees just before the morning fire. Comfortable, warm, stable. If you're fascinated by this survival wisdom that literally saved lives in impossible cold, make sure to subscribe to the channel. We uncover forgotten techniques and knowledge that made survival possible when failure meant death. Hit that subscribe button so you don't miss the next story. The sawdust insulation was performing beyond even Anders's expectations. The 6 inches of packed wood particles created a barrier the cold simply couldn't penetrate effectively. Heat loss was so slow that 5 hours after the fire went out, the cabin was still genuinely warm. The thick insulation on all sides, including the 10 inches of sawdust in the attic, created an envelope that held heat tenaciously. On the morning of January 13th, with outside temperatures still at 51 below zero, James McKinley appeared at Anders's door. He looked exhausted and desperate. "Lindgren, I need help. We're freezing. I'm burning every stick of wood I can find, and we can barely stay above 30 degrees. Can my family shelter here?" Anders welcomed them immediately. The McKinley family, 5 people total, entered the warm cabin from the brutal cold outside. The temperature shock was profound. Mrs. McKinley started crying. They'd been cold for so long, constantly frightened their children would freeze, terrified their firewood would run out. The warmth in Anders' cabin was overwhelming. McKinley stood in the center of the room, feeling the stable warmth. It's 60 degrees in here. Outside is 50 below. How is this possible? Anders gestured to the walls around them. The sawdust, 6 inches between log wall and outer shell. Heat cannot escape through that much insulation. All warmth from fire stays inside. McKinley walked to the outer wall and placed his hand against the board shell. It was cold, almost as cold as the outside air. He walked to the inner log wall. It was warm, comfortably warm to the touch. The sawdust between the 2 walls was preventing heat from reaching the outer shell. The insulation was working exactly as Anders had designed it to work. "You were right," McKinley said quietly. "I mocked you. We all did. Said you were wasting lumber and filling your walls with garbage, but you built the only warm cabin in Minnesota." Anders shrugged. "In Finland, we know sawdust is excellent insulator. Not garbage, is valuable material if used correctly." The McKinley family stayed 3 days while the extreme cold continued. During that time, 2 other families sought shelter when their own cabins became uninhabitable. At times, 13 people crowded into Anders's small cabin. The temperature remained comfortable throughout. The sawdust insulation had capacity far beyond what Anders alone required. Mrs. McKinley asked the question several visitors had. "How much firewood are you using? With all of us here, you must be burning a lot." Anders smiled. "Maybe a bit more than usual, but still very little, perhaps 1 cord per week." Mrs. McKinley's eyes widened. "We were burning 4 cords per week, just my family, and we were still freezing." The children were fascinated by the walls. One of McKinley's sons, a boy of 8 named Thomas, asked if he could see the sawdust. Anders had left one small inspection panel in the outer shell. He opened it, revealing the packed sawdust in the cavity. Thomas reached in and felt it. "It's dry and warm. I thought it would be wet and cold." Anders explained, "The sawdust is protected from weather by outer shell, and it stays warm because it traps heat from inside cabin." The boy pulled out a handful of sawdust and examined it. "It's just wood chips. How can this keep a whole cabin warm?" Anders smiled. "Each tiny piece of wood is surrounded by air. Air does not conduct heat well. Millions of air spaces means heat moves very, very slowly, so heat stays inside instead of escaping." When the cold finally moderated on January 15th, temperatures rising to a comparatively balmy 25 below, families returned to their own cabins. But the experience had transformed understanding throughout the settlement. Anders's sawdust-insulated cabin, the cabin everyone had mocked, had proven itself superior to every conventional log cabin in the region. James McKinley returned home and immediately began planning. Lindgren, before we leave, I need to know, can I add sawdust insulation to my existing cabin? Anders considered. Difficult but possible. You would need to build outer shell around your cabin, then fill cavity with sawdust. Same as I did, but adding to existing structure. McKinley made his decision. That's what I'm doing. This spring, I'll never go through another winter like this. By spring of 1880, McKinley had built an outer shell around his log cabin and filled it with sawdust insulation. Anders helped with the design and construction. The result was a cabin nearly identical to Anders's in thermal performance. The following winter, McKinley's cabin stayed warm with a fraction of previous fuel consumption. His family lived in comfort instead of constant suffering. Word spread throughout northern Minnesota and beyond. Lindgren's sawdust insulation works, keeps cabins 30 degrees warmer than conventional construction. Uses a quarter the firewood. Several families made journeys to see Anders's cabin and learn the technique. Anders welcomed everyone, explained the principles, helped with construction questions. By the fall of 1880, 9 cabins in the region had been retrofitted with sawdust insulation. By 1881, the number had grown to 27. New construction increasingly incorporated double walls with sawdust from the beginning. The technique spread to Wisconsin, the Dakotas, and Upper Michigan. Anywhere sawmills produced waste sawdust and winters were severe, builders adopted the method. A professor from the University of Minnesota visited Anders' cabin in 1882 to study the insulation technique. He took detailed measurements and calculations. His findings confirmed Anders' experience. The sawdust-insulated walls provided thermal resistance approximately 3 times greater than conventional log walls. The fuel savings were proportional and substantial. The professor's report, published in an academic journal, brought wider recognition. Engineers and architects began incorporating sawdust insulation into their designs. The waste material from sawmills became a valuable commodity. Some mills began selling sawdust specifically for insulation purposes. The material that had been dumped or burned was now recognized as superior insulation. The concerns about rot, mice, and fire all proved manageable with proper construction. Rot required sustained moisture exposure. With proper outer shell protection and drainage, sawdust stayed dry indefinitely. Mice required access points. With properly sealed wall cavities, rodents couldn't enter. Fire required oxygen and ignition source. Enclosed sawdust, packed tight with no air circulation, wouldn't support combustion. The few failures that occurred were due to poor installation, inadequate sealing leading to moisture infiltration, insufficient packing leading to settling and gaps. These were construction errors, not flaws in the sawdust insulation concept itself. Properly installed sawdust insulation lasted for decades. Anders's original sawdust insulation remained functional for over 40 years. When he finally renovated in 1922, the sawdust was examined. It was still dry, still maintaining its insulating properties after more than 4 decades. Some had compacted slightly, but not significantly. The material had performed exactly as Anders knew it would. Modern testing of sawdust and woodchip insulation confirms Anders's understanding. Properly installed cellulose insulation, which is essentially processed wood fiber similar to sawdust, achieves R values of R3.5 to R4 per inch. Contemporary builders use blown-in cellulose insulation that works on the same principles Anders applied in 1879. The environmental sustainability of sawdust insulation was remarkable. The material was a waste product that would otherwise be burned or landfilled. Using it for insulation gave value to material that had none. It required no industrial processing, just drying and packing. The embodied energy was minimal, and it came from renewable timber resources. The fire performance of enclosed sawdust is better than most people expect. Testing shows that tightly packed cellulose insulation is difficult to ignite and doesn't support flame spread. Without oxygen circulation, combustion can't occur. Modern cellulose insulation includes fire-retardant treatments, but even untreated packed sawdust has reasonable fire resistance when properly enclosed. Subscribe to this channel to discover more forgotten survival techniques and building wisdom that's incredibly relevant today. From frontier innovations to ancient knowledge, we explore the practical skills that made life possible in impossible conditions. Don't miss the next story. Hit subscribe now. The story of Anders's sawdust insulation teaches lessons beyond thermal performance. It's about recognizing value in materials others dismiss as waste, about understanding that industrial byproducts can be superior to conventional materials, about the wisdom of learning from cultures that develop techniques in harsh climates, about building based on physics rather than appearance or convention. Anders faced constant mockery for building his wooden shell and filling it with sawdust. His neighbors thought he was wasting lumber, using garbage as building material, creating fire and rot hazards. Their mental model of proper construction was solid log walls. Anders's model was physics-based insulation using trapped air in organic material. Until the test came. Until January 1880 brought 54 below zero. Until log cabins struggled to maintain 30 degrees while Anders's cabin held 64 degrees. Until families abandoned freezing homes and found warmth inside walls filled with sawmill waste. Until the evidence proved that sawdust wasn't garbage. It was the finest insulation available. The 30-degree difference wasn't just comfort. In those conditions, 30 degrees was survival. A cabin at 30 degrees with everyone bundled in coats might prevent freezing to death. A cabin at 64 degrees with people in normal clothing meant actual living. Anders's sawdust insulation provided warmth that allowed normal life while others barely survived. The fuel savings were equally critical. Anders' 1 cord per week versus McKinley's 4 cords meant the difference between making it through winter and running catastrophic fuel shortages. The time and danger saved not cutting wood in brutal cold translated to safety and quality of life. The efficiency was transformative. Everyone thought his cabin's wooden shell was crazy. They called it double building, called the sawdust garbage and waste, called it a fire trap and a rot waiting to happen. They couldn't imagine that mill waste could be superior to solid timber for insulation until it stayed warm inside when nothing else did, until their solid log walls failed while his sawdust-filled shell succeeded, because he knew something they didn't. He knew air spaces prevent heat transfer. He knew sawdust structure created millions of insulating air pockets. He knew proper installation prevented moisture, rodent, and fire problems. He knew Finnish forestry wisdom applied perfectly to Minnesota conditions, and he had the knowledge, skill, and courage to build what he knew would work. The wooden shell wasn't crazy. It was sophisticated thermal engineering. The sawdust wasn't waste. It was purpose-designed insulation performing exactly as physics predicted. The double walls weren't excessive. They were optimized for extreme cold. The mockery wasn't wisdom. It was ignorance of superior alternatives. Anders Lindgren's wooden shell with sawdust insulation stayed warm inside when conventional log cabins froze. Not barely warm, genuinely comfortable. Maintained 30 degrees higher temperature than standard construction. Proved that waste materials can be valuable resources. That understanding physics beats following convention. That Finnish forestry knowledge was superior to American building assumptions. They thought his cabin's wooden shell was crazy, until winter proved them wrong, until their log walls conducted heat away, while his sawdust trapped it, until they experienced the warmth inside walls filled with what they'd called garbage, until Anders's sawdust cabin saved lives while their conventional cabins couldn't keep families safe, until the evidence showed that sometimes the crazy-looking solution is the sanest solution available. The wooden shell wasn't a mistake. It was mastery. The sawdust wasn't worthless. It was invaluable insulation. The double walls weren't wasteful. They were the most efficient heat retention system in Minnesota. And the Finnish builder everyone called crazy was the wisest man in the territory, because his cabin stayed warm inside, stayed 30 degrees warmer than theirs, stayed comfortable when they froze, stayed safe when they suffered, all because of a wooden shell filled with sawmill waste, all because he understood that trapped air insulates. That sawdust structure creates perfect air spaces. That waste can be valuable. That old world knowledge can solve new world problems. And that sometimes the person building differently is the only one building correctly for survival.